RLC circuit. In the circuit below, and you'll have bigger pictures on the next slide so you can actually see it, the switch is initially open, all currents are zero, and the capacitor is uncharged. Determine the current and voltage distribution in each part of the circuit immediately after the switch is closed. Then do the same thing for when the switch is closed for a long time. Determine the charge and energy stored on the capacitor and the energy stored in the inductor after the switch is closed for a long time. Then sketch the voltage as a function of time across the capacitor and the current as a function of time in the inductor after the switch is closed. Label asymptotes and go from right when it's closed to a long time later on. Determine the current and voltage distribution in each part of the circuit right after the switch is closed. When the switch is closed, the inductor resists the change in current, so no current will flow through the inductor. However, the capacitor lets a maximum current flow. So we've shown the current path here in red. And now I'll just highlight it in green. It goes like this. Okay. So our circuit is entirely composed now of just the battery, the capacitor, and this resistor here. So the total current will be the battery voltage over this resistor. So it's 1.5 amps. So therefore, the voltage drop across here is also 60 volts. All the voltage supplied by the battery gets dropped there. There's no voltage here or here or here because there's no current flowing. So V equals IR, no current, no voltage drop. So we have a table here to keep track of all the variables. Okay, and the key point, well, there's many key points here, but let's just go. There's no voltage drop across the capacitor. Okay, so these guys, another way of looking at it, they're in parallel with the capacitor, so they have zero voltage drop. So the only action that's going on here is a voltage drop and a current through the 40 ohm resistor, and of course a current through the capacitor. Determine the current and voltage distribution in each part of the circuit after the switch is closed for a long time. When the switch is closed for a long time, the inductor has no voltage drop. It will not oppose the current flow. The voltage drop across the 30 ohm resistor, the 60 ohm resistor, and the capacitor will be the same as they are all in parallel. The capacitor does not let any current pass through it. Our current path now is a little trickier than the previous one. It comes out of the battery, it splits here, some goes through the 30 ohm resistor, and then some comes down here through the 60 ohm resistor, through the inductor, and then back up through this 40 ohm resistor. No current passing through the capacitor. Let's now find the equivalent resistance of this circuit and then the current coming out of the battery. Well, we've got the 30 ohm and the 60 ohm in parallel, so there's their equivalent resistance. And then once you do that, they're both in series with the 40 ohm resistor, so we just add that in. So we get R equivalent is 60 ohms, the current is 60 volts over 60 ohms, 1 amp, and that's coming out of the battery. All of the current flows through the 40 ohm resistor. We'll do the easy one first, and its voltage drop will be I times R, 1 amp times 40 ohms, so that's 40 volts. Okay, so we'll circle that guy. That leaves a voltage drop of 60 minus 40 volts, or 20 volts, across the parallel combination of the 30 ohm resistor, the 60 ohm resistor, and the capacitor. So we're going to lose, okay, we're not losing, it's being transferred elsewhere. 20 volts is going to drop across that parallel combination. Since the 30 ohm resistor is in parallel with the 60 ohm resistor, and of course the inductor has zero resistance, they have the same voltage, which will be 20 volts. To find the current through each one of them, we just divide that by the resistance. And we get the 30 ohm has 0.67 amps, and the 60 ohm has 0.33. And then the current, obviously, through the capacitor, we said that earlier, is zero. And it's good that the currents in the parallel segments add up to the total of 1 amp. And also, this resistance, which is half this one, has twice the current. Also a good thing. We then write the scoreboard for what's going on here, and there's action everywhere except the capacitor has no current going through it, but it does have a voltage drop because it's in parallel with this guy and this guy, and you had 60 volts over here supplied. It dropped, what did it drop? It dropped 20, So then you have 40 volts over here. So that's your voltage drop across the capacitor, 20 volts. Find the charge and the energy stored on the capacitor and the energy stored in the inductor after the switch is closed for a long time. We've got everything we need from the previous slide. So the charge on the capacitor is C times the voltage across it, which is 20 volts, and we get 80 microcoulombs. The potential energy in the capacitor, 1/2 CV squared, 8 times 10 to the minus 4th joules, and the potential energy in the inductor, 1/2 Li squared, and we have 5.4 times 10 to the minus 4 joules. Sketch the voltage as a function of time across the capacitor and the current as a function of time in the inductor after the switch is closed. Label asymptotes. So a sketch you just have to show the shape, and then we added on this asymptote. So we know the capacitor in the beginning has 0 voltage across it, and it rises to 20, and it does with this 1 minus e to the negative exponential shape. We've seen that a bunch of times. So you sketch that, label 20 volts, and you're good. Here's the current in the inductor. We know we start at 0, and we're just sketching it, so we just have to draw the shape, and then it does ask us to label the asymptote. It rises to its value, its maximum value at the end of 0.33 amps, and note it has the same shape as the capacitor charging up.